Okay, so this is question 2 from problem set 2 about projectile motion. The problem says, remember that friend from question 1? Yeah, they're back. They're asking you to play catch again, but you're not really into it. So you go out there and you weakly throw the ball at an angle of 60 degrees above horizontal at a measly 8.5 meters per second. Calculate the horizontal and vertical components of the velocity. I'm always going to ask you to sketch the problem. Here I am sketching it out. You, the friend, setting the origin. Let's get through that sketching and we'll move on with the problem solving. A couple of things noteworthy as you add some detail to your locations in the problem where things are known. So your initial position, y and x, probably is going to be 0, 0. I know that's up off the ground. And later on, if you want to ask like how high above the ground does the ball go, you can always add back in that height. So the initial throwing height I'm setting to be 0, 0 as a convenience. I don't know yet my initial vertical velocity or my constant x velocity. We're going to come down and we're going to do a little bit of right triangle trig to figure those two values out. We'll leave them as question marks right now. Now we're getting into the trig. I'm going to draw that right triangle, and it's going to have a 60-degree angle in the lower left corner, and the hypotenuse is going to be the given velocity of 8.5 meters per second. Yeah, it's 8.5 meters per second. It's always good to reference the problem. So we fill in these values, and now we need to get v sub y and v sub x at the moment the ball is thrown. V sub y is equal to the given velocity times the sine of the angle theta. V sub x is the given velocity times the cosine of the angle theta. Now write those equations down. Side note, those are on the reference sheet, and you should have them with you for all future assessments. I'm going to pick up my calculator here and run those numbers. Find the x and y initial velocities. So in the x direction, that value comes out to be 4.25 meters per second. In the y direction, that comes out to be 7.36 meters per second. This is a great moment to pause and see if your answers are reasonable. I'm looking at the fact that the hypotenuse is 8.5 meters per second. I expect the side length opposite the 60-degree angle to be the longer of the two legs, right? Because it's opening up into a wider space. And I see that of my two legs, purple and green, that is the longer value. 4.25 is the smaller of the two values, and both are smaller than the hypotenuse. It seems to check out. It's probably correct. I'm going to go back into my original sketch and replace those two question marks with these new components of the initial velocity. With these in place, I now have enough information to begin solving the problem for horizontal and vertical type questions. Part B of the question says find the total amount of time the ball is in the air. So I'm going to consider that initial state at the time that the ball is thrown until that final state until the ball is caught. Time in the air is often a calculation done with vertical information. Let's head that way first and see if we have enough information to answer it. Begin with the equation that governs vertical accelerated motion and go and collect all the numbers that we know. Referencing the picture here, I know that y is 0 meters. At the end of the throw, the ball is 0 meters high. Beginning of the throw, the ball is 0 meters high. I know the initial y velocity, and I know the acceleration in the y direction. The one quantity I don't know in this equation is time. Oh, guys, this is going to be a quadratic. I can't solve this by just rearranging numbers and doing some algebra on it. I'm going to either have to graph this to solve it or do the quadratic formula. Now, I love a good graph. I would drop that equation into the graphing calculator and look for the x-intercept in the positive, out in the positive quadrant. But not all of us have graphing calculators. So if graphing does not get you jazzed up, You can solve this using the quadratic formula. Now, my reaction just a moment ago is because, boy, the quadratic formula can lead to some calculation errors. You have to be very careful using it. I've rearranged the equation to put it in ax squared plus bx plus c form, labeled my a, b, and c. And here we go on the quadratic formula. We can do this together, you and me. Well, mostly me. We're going to put everything in the formula before we try doing any calculations. And you can bet that anytime I write this formula out, I am indeed singing the tune, just like you. All right, I'm filling in my A's, B's, and C's, and I'm taking really good care to pay attention to negative signs in the right spots where they belong. What I do now is I'm going to pause here and I'm going to grab my calculator and I'm going to run this calculation. I'm actually going to run it twice just to be extra certain that I've got it right. After having typed everything in the calculator and double checked, yes, I know that in a math context there are two solutions. One of them is going to be positive, and as it turns out in this case, one of them is negative. I can reject that negative solution because that would be a negative some amount of time. I didn't even calculate it because I could see that it was headed in that direction. Reject negative time, right? They don't have a meaning to us. So I'm only going to take the positive solution. Mine came out to be 1.5 seconds-ish. How long is the ball in the air? About 1.5 seconds. That's part B. Now let's go on to part C, asking how far the ball travels out from where it's thrown. Ooh, that's a horizontal problem. Head over to the horizontal column. We're going to start with the horizontal position equation. It looks like I know a lot of stuff in here, so let's see how this works. I know x initial, 0. I know v sub x, 4.25. And as it turns out, I know time, as of very recently, 1.5 seconds. I'm going to run and drop this into the calculator and get what I get. That's around 6.4-ish meters. All right, that question answered. It feels like you're on a roll. That's pretty common. The hardest part in these problems is always setting them up. Find the highest point the ball reached in flight. All right, you got to use your noodle on this one. Highest point, go back to your drawing. Put a dot on at the highest point that the ball will reach. Label that. What are the coordinates of that point? Well, I know that it's going to be half of the x coordinate, and I know it's at y max. I also know that's going to happen at half the overall time of the ball in flight. I know that the velocity at this moment in time is 0 in the y direction. I've labeled all those on my picture, and now I'm going to go set this problem out. If I'm asked for y max, that seems to be something that belongs in the vertical column of my problem. Let's set it up. First of all, I want to write down what I know and what I'm assuming, just to help me keep track of what's going on. What is half of the overall time? Well, if the whole time is 1.5, half is going to be 0.75 seconds. There is a mistake here that I will come back and correct in a moment in the video. So now let's get y equals y initial. You've seen this equation before. Y initial 0. I'm considering just the first half of the journey, by the way, from y initial up to y max. The initial velocity in the y direction, we learned that earlier. The amount of time to get to the maximum point, 0.75 seconds, plus 1/2 at squared. Run that setup through a calculation, and let's see what y max comes out to be. .76 meters, the maximum height above the throwing height, or above the thrower's heads, let's say, is how high that ball's going to go. Now, this problem had 3 parts. We've answered all 3 parts. We're done with it. I'll leave the solution up on screen here if you want to pause and check it out a little more closely. Good luck with your continued future problem solving.